Okay, please welcome the first presenter of these sessions, Arif Fusam Muslim from SEAGC University. He will come to present on the title of the influence of the curing time and temperature on the strength development of the artificial clay with the cement-based binder materials. Welcome, Arif.
Good morning, everyone. Thank you for having me today. My name is Afif Fauzan Muslim. I'm from SEAGC University, currently holding a master study. So today I'm going to present about my research. It's about influence of curing time and temperature on strength development of artificial clay with cement-based binder. So this is today's outline. First, I'm going to show you the background and purpose of the study, material use and method, experimental setting, result of the experiment, conclusion, and also the last, the reference. So, in the deep mixing method, using cement-based binder is extremely important to know whether the quality of soil improve, satisfy the construction standard. In order to ensure the quality, we must take in the soil and test. Sometimes it's 7 days or 28 days. So in these conditions, sometimes it may delay the construction. So therefore, we need an alternative to find solution to make it faster. One of the method in Japan, we call it accelerated curing method with hot temperature. So in this study, we are focusing about to accumulate the knowledge on how soil behave under the hot temperature in accelerating curing method. So this is the material we use. We use two types of soil. First, kaolin and bentonite. And also we use two cement-based binder. We call it US10. It's for soft general soft soil. And then the second one is US20 for high organic soft soil. In the first table is the soil properties. Also, we vary to liquid with distilled water and also salt water to see how the soils behave according to different type of solution. And this is the chemical composition of the cement. So this is the method. First, there are 3 steps. First is pre-curing. We mix in the soils in the mixing machine and stirring, and then after that we put inside the mold with the diameter 5 centimeter and the height is 10 centimeter, and then we do tapping to make sure the homogeneous state. And then we insert into hot water curing, into water curing tank. The maximum for curing time is 21 hours, and we vary with 5, 8, 15, 18, and 21 hours. Also, the temperature is vary from 45 until 75 with the incremental temperature 10 degrees. And after that, 30 minutes after curing time, we do perform an unconfined compression test. So here is the experimental setting. There's 2 big schemes here. First with the, as I mentioned before, the time variation and also for the temperature variation. So there is some constant variable in both schemes. So I'm going directly into the result of my research. This is the result of curing time variation of kaolin. In the first graph, we show the relationship between UCS, curing time and wet density of kaolin with salt water, and second graph with kaolin with distilled water. So both of the graphs showing a same tendency. As the curing time increases, the strength is increased. So from 18 hours, the strength development is relatively small. So we may conclude that this is the highest peak, almost. Next, the second type of the soil. This is the curing time variation for bentonite. Also showing some same tendency as the curing time increase, the UCS value also increase. And also for cement, as cement content is high, also the UCS is also high. And for the wet densities, it shows like there's no significant difference. Next, this is the effect of the salt water on the strength. So here is, you can see two types of soil, distilled water, kaolin and bentonite. In kaolin, the effect of salt increased slightly the UCS value. Meanwhile, in bentonite, it significantly increased. The possible reason due to this phenomenon might be because the diffuse double layer phenomenon, when the high concentration of sodium chloride, it makes the soil particle more thinner. That's why it makes more friction. That's why, and then finally, the UCS value become more higher. And it was significant with bentonite because the capacity of holding water is very high comparing to kaolin. Next, this is the curing time versus the strength ratio. So this is the graph relationship between curing time and strength ratio. What does it mean is comparing QU at 28 days and QU at 5, 8, 15, 18, and 21 hours. As you can see in kaolin, the value is about 2. It means it doesn't close, it means not so close with the QU at 28. If the QU is 1, it means the result is has the same value. But for bentonite, it shows almost close to 1. It means that QU at 28 days can be same with the QU with the 21 hours of accelerated curing method. And it's also significant with salt water. So next, the second variation is about the temperature on soil strength. As temperature increase, the UCS value also increase. And for cement with high organic subsoil, US 20, show a higher strength value rather than US 10. But we can see here the wet density is decreased. One is the possible, after 55 degrees Celsius, one of the possible reason might be because the gassing phenomenon inside the soil void. As the liquid become gas, then it become lighter. Somehow, it didn't affect the shear strength. The reason is still unclear. Next, effect of temperature on soil strength of bentonite. So, as you can see here, it's different with the previous soil, kaolin. After 55 and 65, the soil strength is decreased. The possible reason might be because related to microstructure development of the cement paste. The rapidly forming initial hydration product at elevated temperature, 75, distributedly, heterogeneously, or uneven structure. This lead to higher coarse porosity and reduce the compressive strength. Meanwhile, at lower temperature for 55, the hydration rate is reduced, allowing the dissolved iron more time for diffusion before the hydration precipitate. Hence, the coarse porosity is reduced and the compressive strength is increased. So, for bentonite, this might be the range for maximum strength for the soil improved with the cement. So, this is also the last graph. I will show this for today's presentation. So, this is, as I mentioned before, the maximum is close to about 1.5 for kaolin for the temperature and strength ratio. For the bentonite, as I mentioned before, the maximum is about 55 or 65 degrees Celsius. After that, the strength of the soil become weaker. So the conclusion, in the accelerated curing method with hot water, usage value increase as the time curing increase, both for kaolin and bentonite. Salt water increase the usage value, but significantly for bentonite, and increase of usage of kaolin. Meanwhile, bentonite, the maximum was at 65 Celsius and start decrease afterward. Cement-based binder US20 showing a higher result of USS value than US10. Thank you very much for your attention.
And thank you so much, Hafid, for your interesting topic. Okay, because unfortunately we have no time for the Q&A sessions for each speaker. We're gonna move on the Q&A session at the end of the sessions. Okay, the next one move to the second speaker, Mr. Thanachai Promani from the Kasetsart University, Skonakorn. He will come on the topic of the investigating the suitability of the bentonite sludge from deep foundation constructions for landfill and applications. Okay, when you're ready, please start.
Okay, good morning. And thank you for introduce. ครับอาจารย์ท็อปนะครับ Today my topic is investigating on the suitability of the bentonite sludge from deep foundation construction for landfill application. So like Bangkok, there exists the very thick soft clay layer. So when you construct some superstructure above the soft ground, so they commonly use the ball pile construction. So the key component of the ball pile is the using of the bentonite to prevent the borehole collapse. So after using the bentonite will become a weight, and this research want to evaluate the using of the bentonite sludge is suitable for using of other landfill application or not by using the geotechnical perspective. So let's introduce what is the bentonite sludge and its process. So firstly, we take off the bentonite dredge from the site. After that, we mix with the anionic polyalkylamide. And using our company, SEAGC-AGSSEA, use the centrifuge technique to separate the solid and the water out. And we obtain the bentonite sludge, BS, with the original water content of 70%. And water before discharge to environment, we adjust the pH about 5 to 7 before discharge to the environment. So we start from the material we use. We use the bentonite sludge obtained from the company. And using the bentonite powder, it is the sodium bentonite we use as the control material. And the right-hand side figure show we prepare the specimen for consolidation test. So start from methodology framework. We firstly start from specimen preparation. We oven it and then make the BS to be a powder. Now, firstly, we investigate the chemical physical property of the material. For chemical property, we conduct the XRF and XRD. For physical property, we conduct the Atterberg limit, specific gravity and SIP analysis to use for soil classification under USCS standard. After that, we checking the BS is suitable for using for GCL application or not. We use freeze welding index test, and the value they require should be more than 24 milliliter per 2 gram. If more than, okay, we can suitable use it. And finally, we check the permeability for compacted clay liner application. So we conduct the compaction test and consolidation test. This research, we use the consolidation test to evaluate the K value. And K should be less than 10 power minus 9 made per second. So the result of physical property test as shown in this table for BP or particle passing sieve number 200, while the BS, you can see passing 60%. So the majority of the material was the 5 particle. And some remaining is sand. You can see the figure show the sand particle. And for Atterberg limit, liquid limit, plastic limit, and plasticity index is quite dramatically reduced from the BP. As you can see, about 10 times reduced. BP have a liquid limit approximately 600%, but for BS only 50%. And based on the physical property test result, it can be classified as a high plasticity clay for both soil. For XRF, as you can see in this table, both material have silica and alumina as the main component, and can be say both is the soil. And polymer is not change the chemical component of the material. We use the anionic polymer. So this slide shows the test result of freeze wearing index test. The minimum requirement of the bentonite, which can be used as the core material of this material, it should be have a FSI, freeze wearing index, above 24 milliliter per 2 gram. And the test result is clearly show that the BS provide very low swelling capacity compared to the BP. So based on this slide, I can say the bentonite sludge cannot be used for GCL application. But for the CCL, we firstly conduct the compaction test on this material. The purpose of using this test, we only want to determine the void ratio under the maximum dry density condition. By using this equation, we can obtain the E value of the BS approximately 0.66. So the reason we want to know if we can prepare the sample with the E value, some value, for example, E equal to 0.66, how much the permeability we can get it. So if we conduct the consolidation test by using the Taylor equation, so we can obtain the relationship between void ratio and permeability. As you can see, the solid black show the relationship of the bentonite powder, and the white one show the bentonite sludge. Under the same void ratio of 0.66, you can see BS obtain the K value about 3 times 10 power minus 9 made per second. For bentonite powder, we difficult to determine, so we use the extrapolation test result. And when we compare, we can see the BP provide the K less than about 1,000 times of the CCL, of the BS for CCL material. And for the minimum requirement of the CCL, they require the K should be less than or equal to 10 power minus 9 made per second. So we can say the CCL can be used. The reason is because the above figure, you can see the BP have a monomorionite component, But after we treat using the anionic polyacrylamide, for below figure, you cannot see the montmorillonite. So the montmorillonite, I think you you know, it have the 2-per-1 structure, and between the interlayer have a positive ion, and when water come, it absorb much water. So the reason why liquid limit of the BP is very high. So for the conclusion, based on the physical-chemical property, swelling, and the K analysis, the BS showed a decrease in the swelling and barrier property. And the reduction is due to the anionic polyacrylamide change the clay structure by the fracturation process. And the BS can potentially can be used for CCl material, because under the maximum dye density condition, the K value is less than 1 power minus 9 meter per second. So we recommend it used for water storage irrigation. And by repurposing, using BS can enhance the sustainability in landfill construction and reduce the weight from ball pile construction. For recommendation, if you or I want to extend the research on this topic, so we suggest to assessment both in economic and environment perspective. Thank you very much for your kind attention.
Okay, thank you, Natasha, for the good research topic, you know, to show the attempt how to reuse the bentonite sludge. At least we can see that the good positive result for the CAL applications. Okay, please jump to the third presenter of these sessions, Mr. Natapat Kamsuporn from SEAGC-AGSSEA University. He will come on the topic of the improvement of high water content sludge using ordinary Portland cement as the construction materials.
Thank you very much, Professor, for introducing me and my topics. The objective of these studies were to explore sustainable methods of utilizing waste materials in alignment with principles of zero waste as viewed through geo-environmental engineering perspectives. Let me show the current situations concerning waste generation in Thailand. In 2019, the Pollution Control Department of Thailand reported the amounts of waste in each of the types as shown in this slide. Natural waste was more than 8 megatons per year. Industrial waste was about 21 megatons per year, and municipal waste was approximately 28 megatons per year. In this study, we focused on natural waste. Natural waste that we use in this research is the high moisture content sludge. The first one known as water treatment sludge, I will call it WS. It was collected from dewatering yards of water production plant in Bang Khen, Bangkok. It was compared to the second type seabed sludge, or SS, which originate from the dredging process in second waterway of Bangkok Seaport at Samut Prakan. After collecting this soil, we test the physical properties of them and found that both of them are fine-grained soil and can classify as a high plasticity clay for SS and high plasticity seal for WS. Now move to the chemical compositions of soils tested by XRF or X-ray fluorescence method. We found the result from previous study of Yimsiri in 2018 and Gravik et al. In 2019. The results show that the most oxidized component of both soils are silicon dioxide and aluminum trioxide. The next one is toxic elemental metal test by threshold limit concentrations, or TTLCs, compared to the standard of the Department of Pollution Control in 2015. We found the result from previous study of Ramdamri et al. In 2009 for SS and Metropolitan Waterworks Authority in 2019 for WS. And the results show that these materials were safe to use. Before going, I will explain about NICE criteria that's presented by Nontananan et al. In 19 and 91. This criteria is a guideline for selecting suitable material. N is non-hazardous, I is improvability, C is compatibility or consistency, and E stands for economic. After selecting a suitable material based on their physical property and chemical properties that pass the NICE criteria, we design and select the method to improve their qualities. Because of both soil have high moisture content, so we use combination techniques to improve them. The first step, we made the moisture content in the suitable range, reduce moisture content to 33 to 44 for WS and 109 to 138 for SS. After that, we stabilize the soil with cement at proportions of 150, 200, and 250 kilograms per cubic meters. For the name of the sample, I will call it WSC for water treatment salad mixed with cement, and SSC for seabed red salad mixed with cement. Now let me show the result of unconfined compressive strength. We test the unconfined compressive strength according to ASTM D2166. The results show that an increase of unconfined compressive strength due to curing times. WSC in the red line has a higher strength than SSC shown in the blue line. And both materials give the similar trend to the study of Chumpurat et al. In 2019, that unconfined compressive strength exhibit rapid increase during the initial state of curing time. The unconfined compressive strength increased with decreasing water to cement ratio while using the same amounts of cement but reduce the initial moisture content. In addition, it was also found that increasing the amount of cement without reducing the initial moisture content did not significantly contribute to the development of the strength. The relationship between the unconfined compressive strength and curing time normalized by the strength at 7 days of curing times were proposed following the study by Chumpurat et al. In 2019. They improved the lake-based sediment that is high moisture content slot. We compare WSC and SSC to their result in linear relationships in the semi-logarithmic plots. The slope of the SSC was lower than the others, indicating a slower strength development over time for the SSC. The equations that show in this slide can be used for strength predictions. In the same way, we were able to use strength at 28 days curing time because this is the time when most of cementation reactions is complete. In order to explain strength developments, I will show the X-ray diffraction analysis results. The result indicating that both natural slot has quartz and K minerals, including eulite, kaolinite, and montmorillonite. After the stabilization process, the reactions products such as calcium silicate hydrate or CSS and ethylene were found in both samples. Additionally, the amount of reactions product in SSC and WSC increased from 3 to 7 days of curing, and this trend was consistent with the result of UCS testing. Now move to the internal structure of natural seabed slot that's obtained from scanning electron microscope. This picture with 10,000 magnifications show the organic matter such as small-sized shells, animal debris, and plant debris. In the same way, you will see the organic matter like a plant debris in water treatment slot too. Now let's see the internal structure of soil cement. Left picture is SSC at 10,000 magnifications, and right picture is WSC at 5,000 magnifications. The reaction products observed at 7 days of curing time include CSH gel that appear as breadcrumb shape and rod shape for eating dry. The incorporations of these reaction products in the soil affect to increasing of the soil's density with agreement with XRD results, as well as an increase in soil strength. For conclusions, combinations technique between mechanical and chemical were effective methods for improved high moisture content sludge. The unconfined composite strength at 7 days and 28 days of curing time can be used to normalize and predict the strength obtained at the other curing times. The two types of improved sludge show the similarities in strength development. The strength of WSC was higher than SSC due to the adjust appropriate water-to-cement ratio. The use of lower water-to-cement ratio in the same material can result in a higher strength. The suitable water-to-cement ratio for subbase layers of SSC and WSC should be less than 3.5. Moreover, water-to-cement ratio for landfill liner should be less than 6 for SSC and less than 2.2 for WSCs. The XRD and SEM techniques can confirm the strength development results. The X-ray pattern found that calcium silicate hydrate and ethylene were major reactions product of improved sludge. The same micrograph can express reactions, products, and densifications of soil cements following the strength developments. Thank you very much for your attention.
Okay. Thank you, Natapat, for the good research topic also, in the way that how we can use the sludge and bring it back, for using and apply with the OPC. This is a good one. And please jump to the last presenter of these sessions, Mr. Chalampon from KMUT, North Bangkok. He will come on the topic of the flexural strength properties of the compacted cement fly ash from multiple solid waste, paper propylene fiber sand. Okay, welcome.
Okay, thank you, Mr. Chairman. Good morning, everyone. It's a pleasure meeting you today. Let me introduce myself briefly. My name is Chalampon Wangsampao. You can call me Drip. My affiliation are the Technopark, KMU10B, and the colleagues of the Industrial Technology, KMU10B. My interest about in the topic geophysics and the municipal solid waste and the environmental technology. Today my topic is a flexural strength property of the compacted cement fly ash from municipal solid waste with a polypropylene fiber sand. If you have the question, ask in the end of my presentation. There are my outline of the topic include the first one is the introduction, the second one is the objective, third two research question, fourth is the method, and sixth and the result, fifth is conclusion, and last one the recommendation for the future works. This slide show about the introduction. I know about there was some problem in the fly ash from municipal solid waste. Therefore, I want to investigate about enhancement of the flexural strength of the CCFFS, which is added in the study in the investigate is the benefit on the environmental in Thailand. And the group one show about the cement mining and the cement plant are the cement manufacturing with the coal mining and the coal power plant. There are the release a lot of the carbon dioxide in the group 1 and group 2 to the focus on the material of the landfill or the dump site or the open burning of the waste. That can be the use the RDF power plant and show in this figure show about the fly ash from the municipal solid waste or MSW in short, and fly ash and bottom ash are the of the coal the power plant, and the RDF power plant, the refuse the light fuel power plant can be the mix for the building and the cementing construction material, and the fly ash and bottom ash from RDF power plant can release a lot of the carbon dioxide, methane, nitrous oxide, and the ozone. They are the primary the greenhouse gas. So this is the beginning of the climate change in the Earth. Let's move on. The introduction is continue. This slide show about the process of the RDF power pan, the raw material, show the before the RDF power pan and the fly ash, and to show by using the same method. Let's move on the objective, show about the three objectives of this study. The first one to the study the fly ash, the repayment cement ratio, and the second one to study on the property of the CCFFS. CCFFS in this study is mean the cement compaction using the fly ash from municipal solid waste, MSW in short, and the polypropylene fiber with the sand, CCFFS in short. And the last one to study the CCFFS factorial performance. And let's move on the research question. There are the two research questions of this study. Was how many the percentage can the polypropylene fiber be added into the compacted cement? And the second one, what is the ratio of the cement to the fly ash that can be the maximum factorial strength? And the last one, what is the percentage of the polypropylene fiber that can be the maximum factorial strength? You can see in the relationship with the sand, fly ash for municipal solid waste, and cement, and the polypropylene fiber in the image by scanning the sampling with the high energy beam of the electron. Let's move on to the method. There are the two methods of the study. The first one to the modified Proctor test, and the second one to the factorial strength test in the ASCM. Let's move on. The method is continue show about fly ash per the cement ratio in separate of the group A to group E. Group A the 0 per 100, and group B the 25 per 75 to the group E the 100 of the fly ash and the 0 of the cement ratio with the polypropylene fiber in terms of the percentage as a 0% to the 2%, and the fix of the 5% of the cement by weight. Let's move on. The result is continue to use about the parameter conclusion obtained of the road deflection, the curve adapt to the of the ACM C1609, and you can see the road versus the net deflection show about the percent of the polypropylene fiber in terms of the percent in group A to group E in the 0 to the 2%, and the road deflection curve of the CCFFS with the different fiber content. Let's move the continue to the result. It is to show about the example to use about the analyze show this study use about first peak strength, and peak strength ratio and thickness. And in this study for use about the American Concrete Institute standard. And the last one to the result and the abonic of the cement with the fly ash municipal solid waste, and the polypropylene show relationship with the cement and the sand and matrix and hydration with the sand, cement, and fly ash for municipal solid waste with the polypropylene fiber. And last one, conclusion to the this study to focus on the fly ash versus cement ratio in the 25 per 75, and the fix of the polypropylene fiber in the 1.5%, and fix in the cement in the 5% of the cement by weight. And recommendation of the future work show about the fly ash from municipal solid waste can be the sustainable construction material. The future study should be tried to reduce the quality of the concern use the building and the repairments as much cement as possible with the supplementary and cementation material for the support Thailand the future and the cement demand, while the lowering the cement industrial and greenhouse gas emission. And in this figure show about the RDF is able to reduce the carbon dioxide emission and can control carbon dioxide and the production of the cocaine in the cement industry. And the last one, recommendation to the fly ash for municipal solid waste in terms of the Thailand interpolicy, the BCG, and to this study in scope and the material for the circular economy, and by using the material in the take, the return, use the reuse, repair, recycle to the zero or most of the waste for the enhancement and the functional staying property of the compacted cement fly ash for municipal solid waste. In terms of the industrial waste, the polypropylene fiber for the sustainable process, for the sustainable material, for the sustainable of the construction building. Thank you so much. Thank you for your attention.
Okay, thank you so much for Chalumpon for another good topic. And as the chair of this session, so sorry for the Q&A session because we have to accelerate all up, and now we make a good job because it's just 5 minutes beyond 11:30. But okay, please hang around and jump to the session 2. We're gonna continue on with no break. And as the chair, I would like to end this session and thank you for all participations. Thank you.
Good morning, everybody. Now we move to the session number B. My name is Supakit Nontananan, Kasesat University. I will serve as a chairman and.
Good morning, everyone. My name is Nipon Thirachakumanis from Thai Maruma Industry. I serve as the co-chairman for this session.
Well, for the first presentation, the title of the topic is the topic is changed to a consideration of risk management methods for quality defects in soil improvements with salary bidder presented by Mitsuse Kimihiro-san. Onegai shimasu. Well, we will let the speaker, all speaker present to the last speaker, then we move to the question.
Okay, thank you, Chairman. Nice to meet you, everyone. My name is Kimihiro Mitse. I belong to the Department of Civil Engineering and the Architecture Graduate School of the Science and Engineering, Saga University. Today, I'm going to give a presentation about my study, a consideration of risk management methods for quality defects in soil improvement with slurry binder. Okay, let's start with this. This presentation will be given in this following order: introduction, background and purpose, materials and methods, result in discussion, and summary. Okay, the Saga Prefecture, where I live, is also called the Saga lowland. It has a soft ground consisting of the very soft clay. In Saga Prefecture, the SEAGC-AGSSEA coastal road is currently under construction. The SEAGC-AGSSEA coastal road is a high standard road extending about 55 kilometers from Saga to Fukuoka Prefecture. In Saga Prefecture, the section from Fukudomi Shiraishi Town to Fukaura Shiraishi Town is about to be fully constructed as the Fukudomi-Kashima Road. The SEAGC-AGSSEA coastal road shown in the figure, surrounded by red line, is the Fukudomi-Kashima Road. And background and purpose will be given next. As you can see from these figures, unsolidification of ground improvement occur at a certain place. You can see that the cement has not solidified in the ground and is overflowing to the surface. The cause is thought to be the difference between the mixing conditions in the laboratory mixing test and the actual mixing conditions in the actual equipment at a certain place. And comparing the condition of the unconsolidated cohesive soil at a certain place with that of the soil of the cohesive soil in the lowland of Saga, the soil at a certain place showed lower sensitivity and compressibility, which may have contributed to the quality defects in mixing. In this study, we attempted to simplify quality defect distribution of mixing based on soil sensitivity and compressibility. and the materials and methods will be explained next. First, look at this figure. 36 of 38 boring obtained by December 2021, of which 36 boring are marked with latitude are plotted in Google Earth Pro. We divide this area into areas based on the characteristics such as the depositional environment of the ground. And the road crosses the erosion valley indicated by the red shading. The erosion valley during the sea level rise refers to the trace of the mainstream area of the Ariake Sea when it eroded the land area during the sea level rise. In this study, the road was zoned into the 5 areas. For Area 1 has the deposition of the upper part of the Hasiki Clay Formation. For Area 2 has almost no sedimentation in the upper part of the Hasiki Clay Formation. For Area 3 is a shallow area below the erosion valley during the marine transgression period, and also aberration of the lower part of the Hasiki Clay Formation. And Area 4 is from the Area 3 to the end point in east-west direction. And Area 5 is from north-south direction to end point of the road. And this figure shows the cross-section of the strata of the proposed Fukunomi-Kashima Road construction site. We will discuss the 2 formations that are subject of the study. The upper part and the lower part of the Hasiki Clay Formation consists of the silt sand gravel and high water content and soft. And the Ariake Clay Formation contains the silt mixed with clay and sand. It's also extremely soft. This figure shows the previous figure zone according to the aforementioned policy. Note that the Hasiki Clay Formation and Ariake Clay Formation, which are the subject of the study, are mainly indicated hereafter. The following 3 characteristics of the soil, that is the factors that quality defects can cause. The color to be highlighted in the express as a warning color, and the greater the number of the items corresponding to the item, the darker the warning color becomes, the more likely it is that quality defects will occur. This figure on the left illustrates the study method. Enter the depths in the row direction in Excel and the boring number to the column direction. And then we attempted to visualize the location at the risk quality defects by highlighting the location with the aforementioned characteristics as shown in the figure. The following are the results of the distribution of the liquidity index. It was observed that the areas showing low sensitivity based on their viewpoints were present in each area at a similar depth with the similar distribution patterns, but no noteworthy trends were observed. The following are the distribution results of the compression index. The common feature of the low compressibility soil in area 1 to 5 is that the low compressibility is mainly found in the lower part of the Hasiki Clay Formation. And the following are the result of the organic matter distribution. As a common feature of area 1 to 5, organic matter was found to be mixed in almost all points, mainly in the Ariake Clay and the lower part of the Hasiki Clay Formation. This may be due to the fact that the marine clay is widely distributed in this area, and the Ariake Clay and the Hasiki Clay Formations are mainly marine formations. The final warning color trends superimposing the above 3 factors are shown below. The transition is shown in this figure. The following figure shows that the overlay diagram of the transition of warning color and the subsurface cross-section. In following sections, we will discuss the characteristics that each area exhibits. For area 1, color 3 was observed at some locations, but overall warning color ranged from no color to colored 1. The reason for the color 1 in this area is mostly due to the contamination by organic matter. Area 2 was the most frequently observed area considered to be high risk. The risk of the warning color increases as the Ariake Clay Formation becomes thicker. Regarding area 3, the dominant factor contributing to the warning color is the low compression index. This area exhibits the thicker deposition of the lower part of the Hasiki Clay Formation compared to other areas, possibly due to the erosion caused by marine transgression. The differences between the The difference in deposition environment between Area 3 and the other areas are believed to result in unique variation in compressibility. For Area 4, the frequency of warning color appearing in the lowest among all areas. This means I believe that this area has the lowest risk of quality defects. In Area 5, the meaning behind the warning color indicates is not only the warning level 3, similar to Area 1, but also predominantly relates to the presence of organic matter. Additionally, Area 5 shows the instances of low compressibility in higher elevation compared to other areas. The cross-section of Area 5 extends from the coastal area towards the mountains, which likely leads to the significant variation in soil properties. Okay, this is the summary. The key finding obtained from this study using the method can be summarized as follows. First, the dominant factors contributing to the darker warning colors were presence of organic material and low compressibility. And areas exhibiting low sensitivity based on the liquidity index showed the similar distribution patterns at the comparable depths across all regions. The cross-section of Area 5 extending from the coastal area to the mountains is believed to exhibit significant variations in soil properties. From the perspective of soil sensitivity and the compressibility, it is important to exercise caution regarding the risk quality defect between the local soil and the cementitious solidifier slurry in Area 2, Area 3, and Area 5. That's all. Thank you for listening.
Thank you very much for your nice presentation. Actually, Aliake clay and Hatsuki clay is very similar to soft Bangkok clays, and many research in the past has been done by Professor Miura from Saga University too. Thank you.
The next presentation is geotechnical properties of acetone contaminated bentonite and kaolinite, presented by Leah Loy. Please come on the stage.
Good morning, everyone. Myself, Ria Roy, a research scholar from Indian Institute of Technology, Guwahati, India. And today, my topic of presentation is geotechnical properties of acetone contaminated bentonate and kaolinite bentonite mixture. It's a brief introduction of me. I did my BTech in Civil Engineering from College of Engineering, Trivandrum, MTech degree in Geotechnical Engineering from National Institute of Technology, Surathkal, Karnataka, and currently I'm pursuing my PhD degree at Indian Institute of Technology, Guwahati, India. And my research interest includes environmental geotechnics, pollution control, etc. Moving on to the introduction, as we all know, organic chemicals are considered as the foundation of numerous industries, such as fuel refining, petrochemical complexes, plastic manufacturing, detergent industry, and all. But the improper usage of these chemicals may cause soil contamination. So one of the organic contaminant considered is acetone, and it can cause acute health effects on humans, such as skin irritation, headache, vomiting, dizziness, and it can also affect kidney and liver functioning. So apart from this accidental spills, one of the primary sources of acetone contamination is municipal and industrial discharges from landfills. And from the study conducted by Zhang et al. 2012, it is acetone is considered as one of the top 5 ketones released from raw and aerobically treated municipal solid waste. So in order to prevent this soil contamination from landfills, we have to provide engineered barrier systems to contain this waste or leachate to prevent the further contamination of environment. So compacted clays are being used as hydraulic barriers because of its peculiar properties, such as self-healing ability, low permeability, reliable performance, and cost effectiveness. And it is applied in various applications, such as barriers in waste disposal facilities, and also as a buffer or backfill material in cut-off walls and deep underground repositories. Two commonly used barrier material is bentonite and kyelinate. It has both advantages and disadvantages. Bentonite being a low hydraulic conductivity material, and it has high retention capacity as well. But the problem with this one is chemical incompatibility with organic contaminants and petroleum-based products, and in many Southeast Asian region, there is a shortage of bentonite deposits. And in the case of kyelinate, it has improved workability and reduced susceptibility to desiccation-induced cracking. But the problem with this is it is prone to collapse. So by considering the advantages and disadvantages of both the materials, many researchers have conducted many researches on this for applying in barrier applications. So they have found out that a mixture of 50:50 bentonite and kyelinate can be used as a barrier with a comparable performance in hydraulic performance. So here in our study, we have taken both the materials, kyelinate and bentonite, in a 50:50 dry weight on dry weight basis, and the properties and geotechnical properties of these materials were found out using ASTM standard procedures. This table 2 represents the elemental composition of these both parent materials. And these are some of the results, like some of the basic geotechnical properties such as plasticity properties, specific gravity, pH, maximum dry density, compaction parameters for both bentonite and bentonite kyelinate mixture. And the permeant fluid which we considered is acetone, and the basic properties of this acetone is also given here. Moving on to the results and discussion, first we have considered the plasticity and swelling characteristics of both bentonite and BK mixture in presence of different concentrations of acetone. So we have found that plasticity and swelling characteristics of both the materials, bentonite and BK. We are representing the bentonite kyelinate mixture as BK. And for both the materials, bentonite and BK, the plasticity and swelling characteristics were found to be decreasing with increase in acetone contamination. So when we consider bentonite, BK is also showing a lower plasticity and swelling characteristics because of the less fine content and low montmorillonite content in the kyelinate mixtures. And the main reason for this reduction in swelling characteristics or plasticity characteristics is considered as suppression of diffuse double layer thickness, which is due to the change in the dielectric constant of these materials. So we can just compare the dielectric constant of water, 20% acetone and pure acetone. Like we can see that a higher dielectric constant is observed for water, that is 80.4, and for pure acetone it is almost 20.7. So due to this change in dielectric constant, the diffuse double layer thickness is changing, and due to that change, alteration in diffuse double layer, the plasticity and swelling properties will change. And at higher concentration, the soil fabric can also alter due to this change in diffuse double layer thickness. So next one is hydraulic conductivity. Hydraulic conductivity of both bentonite and BK were also determined using an indirect method, odometer experiment, and it is represented here. First graph shows the variation of hydraulic conductivity with void ratio, and second one hydraulic conductivity at a void ratio of 1.1 with different concentrations of acetone. So here also we can see that acetone contamination in clays, both bentonite and BK mixtures, resulted in the intercalation of acetone molecules in between the clay layers, and as a result there will be a reduction in diffuse double layer thickness, and it can form more flocculated structure. So due to this flocculated structure, there will be flow paths which will increase the hydraulic conductivity of the bentonite and BK mixture. So here we can see from the graph that, like in the case of distilled water, both the materials were showing almost comparable hydraulic conductivity, which is also like found in previous literatures as well. And in the case of higher concentrations of acetone, we can see BK mixtures were showing a little bit lower hydraulic conductivity values than bentonite. This is probably due to the effective distribution of bentonite particles in the pore spaces between kaolin and the resultant pore clogging. So here we can, from our study, we have found a relationship between hydraulic conductivity and liquid limit, as well as hydraulic conductivity and free swell index, and that relationship is expressed in an equation form, and that is represented here. And here we can see, like table 8 represents a comparative performance of bentonite and BK under the permeation of acetone. So here we can see the plasticity properties and swell properties were almost similar at higher concentrations of acetone, whereas we can see that the hydraulic conductivity it is showing a much difference in the case of bentonite than that in BK mixtures. So we can say that swelling characteristics were showing almost similar performance. However, the hydraulic performance, barrier performance was not affected by the addition of kaolinite to the mixtures. And comparative lower chemical sensitivity was observed for BK mixtures than bentonite under higher concentrations of acetone. And here we can support the details of hydraulic conductivity with the help of SEM images. We can see in the DI water, both the materials were showing almost dispersed and undulated flaky structures. And in BK, bentonite particles are filling in the voids, and we can see from the figure, it is a combination of kaolinite and bentonite in BK mixtures. However, in the case of acetone, there is a more flocculated formation is forming, and maybe due to that flocculated structure, there will be more flow paths, and that will increase the hydraulic conductivity. So moving on to the conclusions, we can say that lower montmorillonite content and lesser fine content must be responsible for the reduced plasticity and swelling characteristics of BK compared to bentonite. And acetone contamination is changing the swelling behavior and plasticity behavior of both the materials. And the probable reason must be the lower dielectric constant of acetone. And BK displayed as lesser changes in hydraulic conductivity, probably due to the effective distribution of bentonite particles in the pore spaces between and the resultant pore clogging. We can say that BK is having a better chemical chemical insensitiveness, and we can use, instead of bentonite liners, we can use BK mixtures as a hydraulic barrier in disposal facilities where significant acetone concentrations can be found. And it can also be used as a component in geosynthetic clay liners or compacted clay liners as well. So these are some of the references, and thank you.
Thank you very much for your nice presentation regarding the bentonite, kaolinite, and clay liner.
Well, our next speaker, they are from India. Now we move back to Saga, Japan again. The topic is unconfined compressive and splitting tensile strength of improved SEAGC and SEAGC clay for use as slab. Presented by Matilo Jose Sinite. Please.
Thank you everyone for having me today. My name is Sindete Matiro Jose, and I'm from Saga University. I belong to the Department of Civil Engineering and Architecture, Graduate School of Science and Engineering. Today I will be talking about unconfined compressive and splitting tensile strength of plate-like improved clay. So my country is Benin. I'm from West Africa, and it's a kind of developing country, and we are 12 million people. Right now I'm studying in Saga University, and today I will be talking about unconfined compression strength and splitting tensile strength. And this is the outline of my presentation. From the background, we have the novelty, materials and methods, result and discussion, and finally the conclusion. So first of all, Saga is located in the southern island of Japan, and it's located in this area, as you can see. And this area is known as a very special lowland area with a very soft clay. This clay, I will be talking about more details in the next slide. So this is the geotechnical the positional environment of the clay. So my study will be focusing on this area, the place where we have the clay soil, so the upper parts. So first of all, we have the surface layer, the crust layer, the upper member of the SEAGC clay formation, the Ariake formation, the lower member of the SEAGC formation. And those layers has a specific characteristic based on the clay specification, and I will be mainly focusing on the upper member of the SEAGC formation. So here is basically what's happened when we build something on top of the soft clay, because this clay is known as a soft clay with high compressibility, high sensitivity, with very low permeability. So after embankment construction, we observe some settlements, lateral flow, and plastic deformation. So since several years ago, Chai et al. In 2011, they established a deep mixing method that really improved the soft clay as a countermeasure. So even though we applied the deep mixing method in Saga lowland, we still observe some embankment failure. So in 2004, engineers in Saga lowland, they started applying the plate-like improved clay. Actually, this naming is something that I created with my professor, but this is not the, people usually use the name slab, but when it comes to slab, slab is much more related to construction, building, the slab with concrete and iron and everything. So this is related to soft ground improvement. There is no iron, no gravel. So this is going to be, I will be using this terminology from now on in my research, plate-like improved clay. So by using this plate-like improved clay, these try to take the load of the embankment by focusing on the stretching force. So the tensile strength of the embankment, this will be transmitted to the cement column. So here, engineers in Saga, they have been applying this method. So last time, due to the Kumamoto earthquake and heavy rain, we observed an embankment failure. That was due to these two phenomena. And this embankment failure happened. So engineers started investigating about how to improve more this plate-like improved clay to reduce embankment failure. So my study in the laboratory was focusing on mitigating embankment failure based on the quality control of lab specimen by investigating the strength ratio of unconfined compressive and splitting tensile strength of plate-like improved clay. So here, what is actually the novelty? There is no specific standards related to plate-like improved clay when it comes to construction by applying on the field. So my work here is to help engineers to have more scientific exploration and have to understand the mechanical behavior and performance characteristic for quality control. So here, I would like to really, through my study, help to establish a work standard on the field by providing valuable perception for practitioners and engineers in addressing settlement issue in lowland area. So for the materials and method, this is the soil we use, the SEAGC clay, with a clay content more than 50%, and with a liquidity index IL 1.6 that exceed really 1. And this is really highly compressible clay and very soft. This is the cement we used. They use stabilizer 10, which is commonly used in soft ground improvement. So this is the missing condition. We used the clay and we add the cement with water cement ratio equal to 1. And after 28 days, we use these three conditions: 80, 110, 140 kg per square meter. So for each condition, we obtain 24 specimen of UCT, 24 specimen for splitting tensile test. So this is the missing condition. After calculation, we put the cement, soil, and water in the boil for mixing for 10 minutes. And these are the process from A to I. So A, B, C was performed on the first day. We mixed the specimen based on each ratio, cement ratio, and D was still the first day, and E, F, G, H, I was performed on the 20th day. So for the unconfined compression test, this is the standard compression test, performing the compression test with this dimension of the specimen. And for the splitting tensile test, we apply the Brazilian method, and by doing this, we try to cut the specimen into two by taking care of respecting the length of 0.04 meter to 0.05 meter. And from there, we directly apply the load using the standard compression machine test. And this gives us, based on the formula, we try to calculate, and we obtain the splitting tensile strength of each specimen. So through the material and method as well, we obtain many specimens, and the real question was to examine what is the best way to analyze the data. We obtain from this missing, we obtain the same, from this missing, we obtain the same specimen for QU and sigma T. So which combination should be the best one for the strength ratio? The strength ratio should be sigma T divided by QU. So by having so many discussions with my professor, we finally try to rely on the mean, the maximum, and the minimum value. Of course, by taking into account the coefficient of variation. So here is the result in discussion. So we can notice that as the binder increases, QU and sigma T increases as well variably under the same condition. And this is the condition, the relationship we can observe between QU and each mixing ratio 80, 110, and 140. So still in the result in discussion, we finally rely on the mean, maximum, minimum value. And until now, engineers in Saga-Lolland, they usually consider alpha greater than 0.1, and it has been working until today. But by considering the mean and the maximum, we can see that there are a huge variation between the mean and the maximum. And on the field, when it comes to the application, we need to consider the lower value for a better designing structure. So here, the blue dot is the minimum one, and the red one represents the maximum, and the black one represents the minimum. So result in discussion. So we understood that for reliable alpha, consistency in specimen is really important. I showed in the presentation that we try to consider 0.04 to 0.05 meters for each length. And after discussion, we noticed that by making a standardized length for each specimen, we can have more reliable data and reduce the coefficient of variation in the variation of the data. And this study will contribute in establishing a standard criteria to address fluctuation in alpha. And at last, the conclusion. So as I showed you before, as the binder increases, QU and sigma T increases as well. And by considering the mean, we might have some problem later. So we suggest considering the minimum value of QU, which range between 0.05 and 0.07. Finally, the quality control remains our main objective for this study. Thank you for listening.
Thank you very much for your interesting research topic. Domo arigato.
To the next presentation, the title is the effect of solid waste on sweltering behavior of clay with intermediate plasticity, presented by Apukuma Prajapati. Please welcome.
Thank you, sir. Myself, Apurva Prajapati. I am a PhD scholar from the Nirma University, Gujarat, India. My today's topic is effect of solid waste on swell shrink behavior of clay with intermediate plasticity. So let's go for the flow of presentation. These are the flow of presentation. So first of all, let me talk about the solid waste. There are many solid waste, including sludge, construction solid waste, and many more. But I'm using the construction and solid waste as a stabilizing material of clay soil. So, as we know, the expensive soil is very crucial for any infrastructure. And if we need to use the expensive soil, then we have to stabilize it. So, from the solid waste, we can stabilize it. So, my main purpose is to stabilize the intermediate plasticity clay table, which is classified by the CI soil as per the IS classification. Then construction and demolition waste is procured from the Enviro Project Private Limited, which is the company which collect the construction waste and sieve it and use it as a concrete material. And the properties is obtained and shown in the table. I am using the construction and demolition waste as a sand size. So, for the practical purpose, I am choosing the mixed proportion. The mixed proportion is for the soil and construction and demolition waste. These are the mixed proportion for the practical purpose, which is started from the virgin soil to increment 80%, 20%, 75, 25, and so on. So, first of all, I am conducting the compaction test. For the OMC and MTD, I am performing the compaction test, and from the compaction test, I get the result. First is this graph shows the OMC result. As you see, the OMC result is constant, nearly constant after the 30% of C&D waste is replaced with the soil. And if we go for the MDD, maximum dry density, then we can see that the highest maximum dry density is in the 30% C&D waste. So, from this compaction test, and also I was carried out the triaxial test. So, from both the compaction and triaxial test, I get the optimum doses of the construction and demolition waste as a 30%. So, I compare the contaminated soil with the C&D waste with the virgin soil. So, first of all, the swell measurement, I will go for the free swell index, then oedometer swelling pressure test, then the constant volume swell pressure test. So, for the free swell index, the virgin soil shows the free swell index is 36.36%. And the contaminated soil is showing the FSI value of the 20%. This graph shows the swelling pressure in the oedometer testing. So from the oedometer testing, I was get the result. So we can get the 0 mark for the virgin soil. There is a 60 kPa, and for the contaminated soil, I can get the swell pressure at the 30 kPa, nearly 30 kPa. So from the constant volume swell pressure, I get the same value as the oedometer test. So shrink measurement was done for the sample which is collected from the oedometer testing, and for the few time it allowed to dry in a ambient temperature. Then after I will put it in the oven for the 50 degrees Celsius, and I will measure the volume and the weight in particular time interval. And these are the graph for the shrink measurement. So from this all, the concluding remarks are here. So from the testing, all the tests, I will concluded that the maximum doses for this particular soil is 30%. Then the value of the swell pressure for the virgin soil is 60.83 kPa, and the contaminated soil have a swell pressure 29.63 kPa, which is nearly 51.29% lower than the virgin soil. Then the result indicate that the virgin soil takes the 510 minutes to dry up to the shrinkage limit, and in other hand, the contaminated soil takes the 270 minutes to dry up to the shrinkage limit. So from this all study, I can say that the C&D waste is very, very good for the stabilizing the intermediate plasticity clay. These are the references which I used. Thank you.
Thank you very much. Now, switching to Japan again, our last speaker will present his topic on strength development, characteristic of improved soil with different water smell ratios and mixing times in SEAGC clay, presented by Kazuma Aso from Saga University. 10分間以内でお願いします。
Thank you, Chairman. I am Kazuma So, a first master's student at Saga University, Japan. Thank you. I will now present the strength development characteristics of improved soil with different water cement ratios and mixing times in SEAGC clay. The flow of the presentation is as shown in the slides. First, I will explain the background and purpose of study. I am researching soft ground in Saga, Japan. In the Saga lowlands, the deep mixing method is often used as a ground improvement method. When applying this construction method, W/C is generally set to 1.0. This is because there are concerns about lack of strength and durability due to water addition when improving soft ground. The figure shows the relationship between water cement ratio and confined compressive strength decreases. However, the research group I belong to has a different view on W/C. This table shows data from actual test construction. Compared to W/C 1.0, W/C 1.5 has a higher average QU, lower coefficient of variation, and higher quality.
You did mention that you did some testing on that layer. How well, when you look at in the whole picture, how well does the plate-like improved soil behave when you actually incorporate on top of a deep soil mixing columns? Because I'm not sure whether you have anything to take tensions forces, and I'm assuming, and from your slides, you're adding cements, which is very good in compressions, but how about the tensions, especially between the columns and so on? And how well does it transfer the load to the columns?
Thank you very much for your question. So for this application, we try to apply this from laboratory experiments. So we didn't really go to the field and apply what I've been researching. So here, when we do the embankments, when we have the plate-like improved clay, the strength that is transmitted is going through the plate-like improved clay. And the plate-like improved clay and the cement column are having the same characteristic, the same cement ratio and water cement ratio equal to 1. So they are having the same. So it's like adding an extra layer of cement clay, but in horizontal way. Cement column, but in horizontal way to get the load from the embankment first and transmit it directly to the cement column. So this is a kind of experimental way to have an idea related to quality control of the embankment. Thank you very much.
Can I ask you addition question from his question? Could you please give us some idea on how you decide the thickness of the cement treat slab?
So the dimension of the cement clay, we didn't actually apply on the field yet, but we are using the laboratory specimen. The dimension of the specimen I used, the mold, like 100 millimeter, and the diameter is 50 millimeter to apply first in the laboratory test to see how it behaves. And from there, we can go to the designing structure and try to apply. So like, it might be almost like 1 meter, 1.5 meter of thickness.
I think in the field it's quite difficult to compact and make it in homogeneous materials, right?
Yes, exactly.
But the good way of design is you use the same mixed proportion for the slab and the cement column, yes, that avoid like punching shears, extrude from the columns to the slab.
Yes, exactly.
So good luck for your study.
Thank you very much.
頑張ってくださいね。
ありがとうございます。日本語上手です。
はい。Is there any question? We still have a few questions from the floor, please. Yeah, the topic is very interesting about the cement mixed clay. And one important parameter is the water to cement ratio, as many speakers already mentioned. Still, we have time maybe from my co-chairman.
Thank you, Dr. Supakit. I have one question to the first presenter. As you manage the risk management due to the chart, according to the result that you have the many borehole at a long distance, do you have any recommendations such as in area 2, if I would like to construction in that area, what kind of the extra soil version or what I need to perform more when we know that this area have more difficulty for like organic matter when we need to improve the soil? Yeah, the first, yeah. The consideration of risk management of method for quality defect. Again, okay, according to the result, we have the color map for warning which is area that we have. I would like to know what is your recommendation if, for example, if I would like to construct the road in the area 2 that have a very scattering of the warning color. What kind of the more investigation that I should be performed?
どういう調査をしたらいいか、その質問ですけど。
Okay, thank you very much for your question. So this study is about this. So like for the study, I think we need more like more specific recommendations. Like when we do some improvement to the actual grounds. Oh, wait a minute.
簡単で日本語の説明でもいいです。僕なるべく英語で通訳します。まあその後でもいいです。Maybe it's time for
そうですね。ちょっと実際にどういう現場に対して例えば有機物がたくさん入っていたらこういう控除した方がいいっていうところまでまだちょっと踏み込めていないので、それをちょっと今後にそういうところに発展していけたらいいなと思ってます。
Actually, he said that it's on the state of research. He still don't know how much the organic matters will affect the properties of the treat soil. Okay, that's. 頑張ってください。
Thank you for your translation.
どうもありがとう。
Okay,
That's
thank
all
you very much.
we finish this session, and next session is also important. We have lunch for everybody. Okay, enjoy your lunch and go back to the next session. For me and my co-chairman, we finish our jobs now. Thank you very much, and give big hand to all speaker and audience. Thank you very much.
Okay, thank you very much. The lunch buffet is on the 22.
ผมไม่อยากจะไปลื้อเก้าอี้นี้ให้เป็นแอเรียตากล้อง